Hello there, Mr. Sutton here, bringing you the BC Calculus 8-6 Extra Practice number 2 solutions on polar functions advanced area. On this calculator-based free response problem, we have a figure here showing the polar curves f of theta, which is this inner curve, and g of theta, which is this outer curve here. And I know which one is which, A, because I could do them on a calculator, and also B, because, they said R is the region bounded by the curve of f of theta in the x-axis, so that means this f of theta 1 must be the closer one. Anywho, we want to find the area of R that I was just talking about there. So in general, our area formula, we have the integral from a to b, and a and b, those are just angles, of 1/2 r squared d theta. So in this case, our beginning angle is 0. The ending angle that bounds r, that's going to be pi over 2. So we're going from 0 to pi over 2, all the radius strips in between. And we're going to be doing 1/2 times, well, let's see here. To get r, we just need radius strips of the f function here. So I'm going to do 1/2 f of theta squared d theta. And all of the rest of this happens on my calculator. So to kick things off on my calculator, I'm going to start by putting some things in my y equals. In y1, I've put my f of theta function, 1 plus sine of theta cosine of 2 theta, and I'm expressing everything in terms of x here because that's how these y equals deals work. And then in y2, I put the g of theta function. I don't need g of theta on this part here, but I know I'm probably going to need it later, so why not just put it in there while I'm here. So let me quit out of there now, and I'm going to do math 9 for integral. I've got 0 times pi over 2. And I'm doing, let's see here, 1/2. So let me do alpha y equals, get my fancy fraction, 1/2, great. And now I'm going to do f of theta squared. Well, I stored f of theta as y1. So let me do alpha trace, pull up y1 from that menu, and don't forget to actually square it. And then let me just put an x next to the d, press enter, and that is 0.648. On this part of the problem, they're saying that the ray, theta equals k, where k is some angle less than pi over 2, so some angle in between 0 and pi over 2. This divides S into two regions of equal area. Okay, I'll take their word for it. Right, but don't solve an equation involving one or more integrals whose solution gives the value of k. So my basic idea here is I want to set up an integral for finding the area of S between 0 and k, and I want to set up another integral for finding the area of S between k and pi over 2. So I need to come up with an expression that gives me the area of S. Let's just work on area of S between 0 and k. So using my area formula, I'm going to have integral from 0 to k of 1/2, and now I need an r squared kind of situation. Now to get this S area, I actually need two integrals technically. I need an integral that gives me the area of everything underneath this g curve, and then I need another integral to give me everything under the f curve, and I need to subtract those. So I would have a 1/2 integral of something squared and a 1/2 integral of something else squared, and I would subtract them. Since I'm going on the same interval, though, I could just put those something squareds in the same integral. So here's what I'm going to write. I'm going to go integral from 0 to g of 1/2 of, and now I'm going to do g squared minus f squared. And then d theta, don't forget that. So this gives me the area from 0 to k, whatever that is, of just the S function. I basically found the area all the way from here, and then I subtracted this r piece. So I'm going to set that equal now to another integral from k to pi over 2 of, well, actually the exact same stuff I put over here. So just rewrite all of that stuff exactly, and this now gives me an equation with integrals that I could use to solve for k. On this part of the problem, for each theta they're saying between 0 and pi over 2, w of theta is the distance between the points with polar coordinates f of theta theta and g of theta theta. So write an expression for w of theta and then find the average value of w theta over the interval from 0 to pi over 2. All right, let's start with an expression for w of theta, which they said is the distance between these 2 points. Basically, this point right here, f of theta comma theta, this is your distance from the origin here to the f function. And g of theta comma theta, that's the distance from the origin to the g function. Well, if you're at the same angle, those are basically like two lines that one is just an extension of the other. So if you want to find the distance between these, you really just need to do the g function of theta minus the f function of theta. So that's what w of theta is going to be, just basically g minus f. They just kind of covered it up by making it sound all confusing there. So now we want to find the average value of this thing over this interval. So we're just going to use our standard average value setup, 1 over the interval length, so 1 over pi over 2 minus 0, times the interval from 0 to pi over 2 of the thing we're trying to average, which is just w of theta, d theta. And since we already defined w of theta right here, we can just write it in here. And now I can just actually solve that on the calculator because I already have g of theta and f of theta defined. So I can use those on the calculator without showing any further work. So to make this actually happen on the calculator, I need to define w on here, or at least it'd be helpful. So that was g minus f. So alpha trace y2 minus alpha trace y1. There we go. And let me quit out of there now. So now I'm going to do basically 1 over pi over 2. So let me do fancy fraction, 1 on top, and down below we're going to do another fancy fraction. This is kind of overkill. I could just do 2 over pi, but whatever. So let me do pi over 2 down here. My calculator will same change flip for me because I'm so lazy. And now we have the integral, math 9, from 0 to pi over 2 of, and now we have to integrate w, which I have conveniently stored as alpha trace y3. Put an x there next to the d. Hope for the best. Press enter. 0.485. For the last part of this problem, using the info from part C, we want to find the value of theta for which w of theta equals the average value of w. And we also want to know if w is increasing or decreasing at that value. All right, so let's go back to the calculator. So here's what I did on part C. I just found that average value. Let me go ahead and store that as a constant here. Not a variable, it's a constant. So let's see here. Let's use w. Seems like a good one. And press enter. All right. So now we're going to figure out where the w function equals this constant. So to do that, let's go to y equals. Remember, we had w stored as y3, so I certainly don't want to have y1 or y2 selected. I just want to graph w along with that constant that I just stored. So we're going to put alpha w in as y4. And we're going to go ahead and graph this using the same interval we used before. So that was the interval again from 0 to pi. And let's do a zoom fit, zoom 0. See where these things intersect. So here's w from 0 to pi. And this next one is going to be the average value of w right there. So let me go ahead and see that intersection point. And actually, I want to zoom in a little bit more there. Let me go a little bit closer. Let me do pi over 2. And then zoom fit again. I just want to make sure we're not crossing twice. We probably aren't because they said find the value for which value of theta, for which w of theta equals the average value of w. But you never know. Okay, we're not crossing twice. This is good. So let me do second trace, not table, second trace, option 5. And then move my spider closer to that intersection, enter, enter, enter. And that happens at about 0.5177 if we round that off. And I'm going to call that value that I just found when I solved this on the calculator, I'm going to call that value Q. And I'm going to store it on the calculator so that I can call it back whenever I need it. So we'll go down to store, and we'll do alpha Q. I feel like I'm storing a lot of things on the calculator for this problem. All right. So we wanted to figure out is W increasing or decreasing at that value of Q that we just found? Well, we basically need to know the sign of W prime of Q then. So let's go ahead and plug that into the calculator. So in order to take the derivative at W, the good news is we don't need to write out the derivative algebraically, since we're just taking the derivative of a function that we've already defined earlier in part C. At a single point, we just have to use the calculator. So we'll do math 8 dx, and I want to take the derivative of W, so alpha trace y3. And then we want to do that at Q, so alpha Q, and then enter. Gives us negative 0.5819, or 0.582, however you want to round that off. Now the key here is that this is negative, therefore W is decreasing at that value of theta, that Q value. For this problem, we have a polar equation here given by R. And let's see, this is on the interval from 0 to pi. We want to know, for the first part of this, what the area bounded by the curve and the x-axis is. So I'm going to go on my calculator and enter a few things in here. Specifically, in my y equals, in y1, I've entered this original R function, which I'm actually going to call f, just because R seems kind of generic. It's kind of like saying y equals something. So when I'm talking about f of theta, I'm talking about this R function specifically. And in my y2, I also entered dr over d theta, this function here, which I'm going to refer to for most of this problem as f prime of theta. Again, just so I'm being as specific as possible, and now I can use the names of these functions without worrying about people not knowing what I'm talking about. So again, for my first task on this, I'm trying to find the area bounded by the curve and the x-axis. So I'm going to use my area formula, integral from a to b of 1/2 r squared d theta. So my interval here, I'm going to be going from, it looks like 0 all the way to pi. So we have the integral from 0 to pi of 1/2 times this curve here squared. So 1/2 times f of theta squared, d theta. And now I can just put that in the calculator, the way it's written pretty much. So here's what this looks like on the calculator. I did math 9 for integral. We're going 0 to pi, 1/2. And again, I stored f of theta, the r value, as y1. Just don't forget to actually square that in there. Press enter, and this comes out to about 4.382. For this problem, our task is to find out the angle that corresponds to the point on the curve with an x-coordinate of -2. So basically, what angle is this at right here? So to figure this out, the equation I'm going to use is just one that relates x values and angles. We know that in general for polar coordinates, x is going to equal the radius times cosine of theta. So I can write here -2, which is my x value, equals my radius, which is just the f of theta function that I wrote about earlier, times cosine of theta. I'm just going to go ahead now and solve this on the calculator. So to solve this, I'm going to go into my y equals, and in y3, I'm going to create this f of theta times cosine of theta function. So f of theta, again, that was y1 where I stored that. Let me do alpha trace y1. And we got to be careful here, because if you just put a parentheses next to this and put cosine in it, you're plugging cosine into y1. But if I just write cosine with no parentheses, then I'm multiplying. So you got to be careful with the syntax on these functions here. And then we do x in there. So this is f of theta times cosine of theta. And I need to see where that intersects -2. So I'm going to go down to y4, and I'm going to put -2 in there, just a constant horizontal line. And as one last thing, I'm going to deselect y1 and y2, because I don't really want to graph them at this point. I just want to graph these other two functions. And I want to do this on the window from 0 to pi. So let me go to window, and I'll put 0 as my x min, and pi as my x max. And now let me do zoom 0, zoom fit. See where these things cross. And I mean, I could probably have done pi over 2 to pi as my window because I know this is going to happen somewhere out here. But hey, who's keeping track? All right, so there's the intersection. Let me do second and trace and option 5 for intersect. And let's see, enter, enter, enter. And that looks to be about 2.786. For this part, we're told that between pi over 3 and 2 pi over 3, dr over d theta is negative. All right, we'll take their word for it. We want to know what this says about r and the curve in general. So on the interval from pi over 3 to 2 pi over 3, there's two things that are true. First off, just looking at the r function in general on this interval, r is theta plus sine of 2 times theta. So it's theta plus a sine of something. Now on this interval, theta, which the smallest value on this interval is going to be pi over 3, pi over 3, pi is a little bit more than 3, so dividing that by 3, you're going to get a number that's a little bit more than 1. So you have a number that's a little bit more than 1 plus sine, and sine can't be any less than negative 1. This means that r is always going to be positive on this interval from pi over 3 to 2 pi over 3. So r is going to be greater than 0 on the interval, and they already gave us that dr over dt, the change in r, is negative. This tells us two important facts. The fact that dr over d theta is negative, regardless of the value of r, tells us that r is decreasing. But now the fact that these two things are having opposite signs or working against each other, that r is positive while r is decreasing, this further fact tells us that the curve is getting closer to the origin on this interval. R is essentially your distance away from the origin. So if that's positive and it's going down, that means we're getting closer. Now, it was important to note that the sign of r was positive because r can have a negative sign, which is essentially like walking a certain distance facing backwards away from the origin. So if r had been negative and dr over d theta were decreasing, well, then it would be negative and getting more negative. You'd essentially be walking backwards further and further away, and your overall distance would also be increasing at that point. But because these two had opposite signs, we can definitely say the curve is getting closer, which is what it looks like is happening visually at that spot. For this last part of the problem, we want to find the value of theta on the interval 0 to pi over 2, giving us the point that's the furthest away from the origin. So furthest away, because r could be positive or negative just in general with the way these polar curves work, furthest away means we're looking for the highest absolute value of r. So if we have a negative that has a higher absolute value than a positive, then that one's going to win. So we need to basically find the absolute min and the absolute max for r, and then compare them. And by r, I'm talking about this function right here, which we called f of theta earlier on. So we're going to have to do the candidates test for this. We're going to test out the endpoints here, 0 and pi over 2. And we're also going to test out any critical values that occur on this interval. To find those critical values, I'm going to take dr over d theta, which I've called f prime, just to make it really specific, and I'm going to see where that has a value of 0. We don't have to worry about it being undefined because cosine isn't undefined anywhere. But let's check this out on the calculator. So here I am in my y equals, and I'm going to deselect some of the things I graphed earlier in part B, and I'm going to reselect now this y2 function. This is where I stored my, my f prime, and I want to see where that crosses the x-axis. Now I have to adjust my window. I'm going to go from 0 to just pi over 2. I'm not really interested in anything else. Zoom 0 now, and let's see where that crossing happens. So it looks like it's going to happen right about here, almost at 1 maybe. Let me do second trace, option 2 for zeros, and let me click enter a little bit to the left and a little bit to the right, and then one more time to get my value of 1.0472. There we go. And I'm going to call that Q so that I can refer to it easily and not have to write that ever again. I'm also going to store that value on my calculator. So quit out of that graph, and I'm going to press the stow button, which immediately stores whatever answer I just got. As I'm going to go with alpha Q. I mean, you can do whatever letter you want, but I'm thinking Q for this problem just because. So now it's time for the candidates test. This was our only critical value for the f function. So now I have to test out that critical value along with my endpoints 0 and pi over 2. So to test these out, I'm just going to plug each of them into the f function, this original r function here. So let me do f of 0 to start with. To do that, I have to do alpha trace, and I'm going to go with y1 because that's where I stored f. Plug in 0, and that comes out to 0. Okay. Well, that's probably not going to win. Let's do f of q next. So let me just yank my input from before, and now I'm going to replace 0 with alpha q. Enter. 1.913 and some change. And then finally, we'll do pi over 2. So yank the input from before, replace that with, let me go with pi over 2. And that comes out to about 1.5708, I guess, if I take it out to 4 decimals. So out of the three of these, 1.9132 is the furthest away from 0, has the highest absolute value. So we would say then that the theta value at which we're furthest away from the origin is going to be Q, 1.0472.